Welcome back, OS enthusiasts. This is Victor, and you're tuned in to Operating Systems Crashcast. Today we're diving into some fascinating synchronization examples that are not only crucial for understanding operating systems but also popular in technical interviews.
That's right, Victor. I'm Sheila, and I'm excited to explore these classic synchronization problems with you. Before we jump in, let's quickly recap what synchronization is all about.
Great idea, Sheila. Synchronization in operating systems is all about coordinating the actions of multiple processes or threads to ensure they work together correctly and efficiently. It's crucial for preventing race conditions, deadlocks, and other concurrency issues.
Exactly. Now, let's start with our first example, the bounded buffer problem, also known as the producer-consumer problem. Victor, can you set the stage for our listeners?
Certainly. Imagine a factory where workers are producing items and placing them on a conveyor belt, while other workers are taking items off the belt to package them. The conveyor belt has a limited capacity. That's our bounded buffer.
That's a great analogy. In computing terms, we have producer processes or threads that generate data and consumer processes or threads that use that data. The challenge is to synchronize their actions when the buffer has a fixed size.
Right. The key issues here are ensuring that producers don't add items to a full buffer and that consumers don't try to remove items from an empty buffer. We need to use synchronization primitives like semaphores or monitors to solve this.
Absolutely. This problem is particularly relevant in scenarios like print spoolers, where print jobs are produced by applications and consumed by printer drivers. Now, let's move on to our second example, the readers-writers problem.
The readers-writers problem is fascinating because it introduces a new dimension to synchronization. Instead of just producers and consumers, we now have two types of processes that access shared data differently.
That's right. Think of it like a collaborative document. We have readers who can access the document simultaneously without issues, but writers need exclusive access to make changes. The challenge is balancing efficiency and preventing starvation.
Exactly. In real-world systems, this could be a database where multiple processes can read data concurrently, but updates need to be done exclusively to maintain consistency. The tricky part is deciding how to prioritize readers and writers.
Indeed. There are variations of this problem that prioritize either readers or writers, each with its own trade-offs. It's crucial to understand these trade-offs when designing systems that involve shared resources with different access patterns.
Now let's tackle our final and perhaps most famous example, the dining philosopher's problem. Sheila, would you like to introduce this one?
Of course. Picture 5 philosophers sitting around a circular table. Each philosopher has a plate of spaghetti in front of them and a fork between each plate. To eat, a philosopher needs 2 forks, but there are only 5 forks total.
This scenario, proposed by Edsger Dijkstra, beautifully illustrates the challenges of resource allocation and deadlock prevention. Each philosopher represents a process, and each fork is a shared resource.
The crux of the problem is that if each philosopher picks up the fork to their left simultaneously, we end up in a deadlock. No one can pick up their right fork to start eating.
Exactly. This problem is particularly relevant in operating systems when dealing with multiple processes competing for limited resources. The solutions often involve techniques like resource hierarchies or introducing an arbiter.
It's worth noting that while these problems might seem abstract, they represent real challenges in concurrent systems. Operating systems, databases, and distributed systems all face variations of these synchronization issues.
Absolutely, Sheila. Understanding these problems and their solutions is crucial for designing robust, efficient, and deadlock-free systems. They're also favorite topics in technical interviews, so our listeners would do well to study them in depth.
Great point, Victor. To recap, we've covered the bounded buffer problem, which deals with producers and consumers sharing a fixed-size buffer. We then discussed the readers-writers problem, highlighting the challenges of managing different types of access to shared resources. Finally, we explored the dining philosopher's problem, which illustrates deadlock and resource allocation issues.
That's a great summary, Sheila. These problems showcase the complexity and importance of process synchronization in operating systems. They're not just theoretical. They have real-world applications in everything from multi-threaded applications to distributed systems.
Absolutely. And with that, we've come to the end of today's episode. Thanks for tuning in, everyone. Keep those processes synchronized, and we'll catch you in the next episode of Operating Systems Crashcast.
Until next time, happy computing.